Hello everyone, good evening. So I think we are meeting after some considerable amount of break. So we'll start from where we have held the session on the refraction. So we have completed up to the reflection part, and we are going to start with the refraction. See, like from these ray optics, right? We'll make a separate video on the derivations. So we have some derivations for the reflection part, especially the spherical mirrors. We have some derivations. Those derivations as well as the derivations that we'll have in the case of lenses. All those derivations will make a separate video so that you can go through it, because the derivation for the lens maker's formula that we are going to get in the lenses, right? So those things will be needed for you in terms of your board exam preparation. Okay. So today we are going to start with the idea of the refraction, and here again we have a good amount of scope for getting questions more than reflection, right? Because the level of application that is possible in reflection will be limited, but refraction we can have like various combination or areas where we'll get questions from. So today's session, right, we'll begin with the basic idea of the refraction. See, refraction phenomena will come into effect when we are talking about the light rays moving from one medium to another medium. See, here we have medium 1, we have medium 2. Let us say we are incidenting the light ray. So we are incidenting the light ray from the medium 1. We are incidenting the light ray normal to the surface. So there is a surface between the medium 1 and medium 2, right? So we are incidenting the light ray normal to surface. If you do that, right, then what we will see, this is the general observation. See, all these laws, everything, right, they are basically proposed to explain the observations. So what will be observed is the ray will just go like that. So the ray will just pass along the same normal. This is what will be observed whenever we are incidenting a ray. We call it as what? Normal incidence. Same concept we have seen in the case of the reflection also. Okay. The difference is what? In case of reflection, if it is a normal incidence, means what did we study? Normal incidence means what? The reflected ray will just turn backwards. So that is what we have seen in the case of the reflection. Now here what will happen in the case of the refraction? We will see that the ray will just go along that same normal. Okay. But if we incident the ray making some angle with the normal, instead of giving it normal incidence, if we incident the ray making an angle with the normal, okay, like look at this one. So this is the normal, right? So this is the normal. I'm just drawing the normal line. So we are making some angle with the normal. Let us call it as what? The angle of incidence. Then we would not usually see that the light ray will go in the same path. So this is the same path, whatever the original path of the light ray, right? Light ray will not usually go that way. It will go that way in the rarest of the rare cases. I'll tell you what is the reason for that also. Generally what we will be observing is light ray will be bending away from the original path. Okay, so it will basically move away from the original path. And in this there are two possibilities. Look at this, I will show one possibility. Like if the light ray after entering into the second medium, if it is going like this, let us call it as what? The possibility 1. Okay, I will show you one more possibility. The other possibility, let us represent it like this. This is another possibility. This is possibility 2. So when we say that no, it is not going in the same path, means either it will bend this way or that way. So how do we understand the bending of this light ray? We will understand this with respect to the normal. See, in possibility 1, what do we see? It is actually bending towards the normal. In that possibility 1, it is bending towards the normal, correct? What about the possibility 2? You see what is happening? It is bending away from the normal. So in the possibility 2, what is happening? It is bending away from the normal. So this is what is going to happen. So whenever we look at the light ray entering from one medium to another medium, what we will generally see, either it will be bending towards the normal, that will happen in some cases, or it will bend away from the normal, that will happen in another set of cases. But how do we know in which case it is going to bend towards the normal, or in which case it will be bending away from the normal? This we will be able to understand when we learn about a property of the medium, which we call as the refractive index. So this property, right, is something that we have studied in our lower standard, 10th standard also. I'm sure you would have seen this refractive index. How do we calculate the refractive index? All these things you would have seen. But this refractive index, right, is what we call as it's an optical property of the medium. Like in our electrostatics and magnetism, right, we talked about permittivity. Permittivity is what? Electrical property. Permeability, that is related to magnetism. What is permeability? It talks about how the magnetic field will penetrate through medium, right? Permittivity talks about how the electric field will penetrate through medium. Similarly, here we have optical property, which we call as refractive index. First we will understand the refractive index, then we will see how the refractive index will determine whether the light ray will be either bending towards the normal or away from the normal when it is entering from one medium to another medium. Okay, so we'll look at what is the refractive index. Any medium, right, when the light ray is entering into the medium, its speed will be lesser than that of the speed of the light in the vacuum. So when we say light, the same concept can be used for all the electromagnetic radiation. We are using the word light, but the same phenomena can be used for all the electromagnetic radiation. So whenever we look at the comparison between the speeds, we can take a ratio. So speed of light in vacuum divided by speed of light in the medium. This ratio, right, will be what? It will be more than 1, because what are we saying? The speed of the light in the medium will be always lesser than the vacuum speed, and we know what is the speed of light in vacuum. Approximately what is it? 3 into 10 power 8 meter per second. So this refractive index, right, for any medium will be what? More than 1, and it will be a property of the medium. It will change from medium to medium. Like if you take glass, it may have a refractive index of something like around 1.5. You take some other medium, water, it may have a different refractive index. So the refractive index will change from medium to medium. So from here what we can say, the relation is what? C will be equal to what? Mu into V. C will be equal to what? Mu into V. Okay. Now on this formula, right, like maybe in the 10th standard level you can expect questions, but here we will not be able to get questions on this particular formula. Okay. But when we talk about the refractive index, right, here this mu, right, is also called as absolute refractive index. So that is what the refractive index of the medium that we measure when we compare the speed of light in the medium with the speed of light in the vacuum. That is why we call it as what? Absolute refractive index. There is one more quantity or term called as relative refractive index. Okay. So relative refractive index is also sometimes worded like this. Okay. Say for example, look at this wording. We say refractive index of medium 1 with respect to medium 2. So this is how sometimes we will see the wordings. It means what? It simply means refractive index of medium 1, mu 1, divided by refractive index of medium 2. This is what we call as what? The refractive index of the medium 1 with respect to medium 2. Simply we have to divide both of them. That's it. Okay. Now when we say that, okay, so when the light is going from one medium to another medium, so now we understand that the speed of light will be different in different medium. So look at this. So we have here medium 1 and we have here medium 2. When light is going from one medium to another medium, here the speed is v1, here the speed is v2. What other properties of the light will change? See, speed of the light is dependent upon what? Wavelength and frequency, right? Speed will depend upon what? Wavelength into frequency. So speed, not just light for any wave, right? Speed is equal to what? Wavelength into the frequency. Now frequency will depend upon what? The source. Because if the light is originating from a source, the number of cycles given per unit time, that will depend upon the source. Which means when the light is entering from one medium to another medium, we clearly see that the speed will change. But the frequency will not be changing, because it is after all depending upon the source from where the light is coming. If the frequency is not changing, then we are saying speed is changing, right? Frequency is as it is. So the change should be reflected in what? The change in the wavelength. So the speed is changing, right? That will be reflected in terms of what? Change in the wavelength. So when light is moving from one medium to another medium, what is going to change between wavelength and frequency? Frequency will not change, only the wavelength will be changing. So here the wavelength is let us say lambda 1. Here the wavelength will be different. Okay. Now we can understand the relation between the wavelength and refractive index, just like the way we have the relation between speed and the refractive index. How? Just look at it. Okay, what is it? The speed of light in vacuum means what? Frequency into, in vacuum, let us say the wavelength is what? Lambda naught. Okay, divided by speed of light in the medium means what? Frequency into, here in any medium, let us say the wavelength is what? Lambda. So frequency is cancelled. So refractive index, right? We can also understand it like this. What is it? Lambda naught by, maybe I'll just erase some part of it and write. So in terms of the wavelength, this will be useful for us when we go to the wave optics. So wave optics, we'll talk about certain experiments. The experiments where we'll try to understand the interference and diffraction phenomena. So in those cases, right, these relation between the wavelength and the refractive index will be useful for us. So look at this. Refractive index mu can also be understood in terms of the wavelength. What is it? It will be lambda naught by lambda. What is lambda naught? Wavelength in the vacuum divided by lambda is what? Wavelength in the particular medium. Okay, so this is how we will see the relation in terms of the property of the light when it is moving from one medium to another medium. Okay, now if you look at this mu value, right, mu suggests what? How fast or how slow the light is going in that medium. See, if you look at it, mu is higher means what? Look at this, mu value is higher means what? The denominator must be less, means what? In that particular medium the speed will be what? Less. Mu is lesser means in that medium the speed will be more. Okay, so depending upon the refractive index, we will be able to know in which medium the light will be going faster, in which medium the light will be going slow. Okay, and wherever the speed is more means what? Because the frequency is not changing. No, wherever the speed is more means what? There the wavelength is more. Wherever the speed is less means wavelength will be less. Okay, so speed and wavelength, direct proportional relation, because after all that is the relation, right? Speed is equal to what? Frequency into wavelength, proportional relation. But when it comes to the refractive index, it will be what? Inverse. The relation will be what? Inverse. When the refractive index is more, the corresponding medium speed of the light will be less. Like, to give you a very simple example, right, I'll tell you there are two mediums. Okay, maybe you can just type the answer in the chat window. There are two medium. One is having a refractive index of 1.5, other one is having a refractive index of 1.8. Now can you quickly tell me in which medium the speed of the light will be more? Look at these values. What is the relation? Wherever the mu is less, speed of light in the medium will be higher, which means what? 1.5 and 1.8, where the mu value is lesser, mu is lesser in 1.5 case, right? Which means what? In this medium the speed will be higher. So this is how we will understand the relation between the properties of the light when it is moving from one medium to another medium. Now let us look at it in terms of the understanding of why this bending of the light is happening when it is moving from one medium to another medium. What did we say? The bending of light is happening, right? So why is this bending of the light happen? So just look at it here. We have taken two medium 1 and medium 2. By looking at the representation itself, we can understand one thing. So look at this length. It is appearing higher to be than the lambda 2. Means what? Here what do we see? Lambda 1 is more than lambda 2. That is what we see, right? What do we observe? Lambda 1 is more than lambda 2. Means what? V1 will be more than V2. If you call the refractive index of the medium 1 as mu1 and the medium 2 as mu2, right? Then remember, the relation in terms of refractive index will be inverse, right? Means what? The mu1 value will be lesser than mu2. We see that lambda 1 is more than lambda 2. Means what? V1 will be more than V2. But in terms of refractive index, it will be the inverse relation, right? Mu1 will be less than mu2. Now when the light is moving from one medium to another medium, so this is the medium 1, this is the medium 2. Here what do we see? The speed of the light is more in the medium 1. In this particular case, what do we observe? The speed of light is more. Now this is the normal. Okay, so this is the surface and this is the normal line. Okay, now we are incidenting a light. So in the medium 1, the speed is what? More. Medium 2, the speed is getting lesser. So light would actually, so I'll draw a original path. This is the original path. This is the original path. Okay. So since in medium 2 the speed of the light is getting less, light will take a path which will be shorter. So what do you mean by taking a short path? Taking a path which is shorter. Look at this. Always the path which is close to normal will be shorter path. Look at this. So if it goes in a path which is close to normal, right, that is going to be a shorter path. So which means when the light is entering from a medium, here you see that here what is it? The refractive index. The refractive index is less. What is observation? Mu1 less than mu2, right? Refractive index is less. Into a medium where the refractive index is more. So we use certain terms like, whenever for a medium, right, the refractive index is less, we will call it as optically rarer medium. What is the word that we say? Optically rarer medium. When the refractive index is more, we will call it as what? Optically denser medium. So since the denser medium, right, denser means, don't think of it in terms of physical density. Physical density need not have direct correlation with the optical density. Just because we have a substance where the physical density is more, need not mean that the particular substance will also have a higher optical density. This point we have to be clear. Okay, this density we are talking is in terms of what? The optical density. So when light is moving from rarer medium means what? The medium for which the refractive index is less, to denser medium. Denser medium means the refractive index will be higher. So speed of the light is getting reduced, so it will take a path close to normal. That will be the shorter path. Okay, so now we understand in which case the light will be bending towards the normal. Okay, now what is the other possibility? The other possibility will be when the light is moving from a denser medium to rarer medium. So what we have seen so far is what? The case 1. Case 1 is what? When the light ray is bending towards the normal. That is what we are able to understand through this example. Okay, what will be the second example? Second example is what? If you take, this is the surface and let us say this is the normal. So here we incident, this is the denser, right? This is medium 1, medium 2, same scenario. So medium 1 is what? Optically we'll say what is it? Rarer, because mu1 value is less. Here what is it? Optically denser one. Okay. Now we incident a ray from that second medium, means the ray is coming from medium 2. The ray is coming from medium 2. Now this would have been the original path. Okay, but when the light ray is coming from the denser medium to rarer medium, what is happening? In the rarer medium, right, speed of the light is what? More. Speed of light is what? More. So it will take a longer path. See, longer path means what? It will be always away from the normal. So when you go close to the normal, right, in that particular medium, let us say you have a medium of this much thickness. You want to cover, like this is what? Covering in the shortest path means what? You go exactly along the normal. You go far away from normal means what? You are taking a longer path to cover that medium. So here what do we observe? It will be what? Bending away from the normal. So when it is entering from denser medium to rarer medium, what do we observe? The light ray will be bending away from the normal. Okay. So this is what we'll have in terms of the possibilities of when the light ray will be bending towards the normal and when the light ray will be bending away from the normal. Okay, so these things we have to keep in mind. So this is it. So this is how we will be able to understand when the light rays will be bending towards the normal and when the light rays will be bending away from the normal. Okay, so just look at this relation here. So what will be the relation we'll have between the refractive index values and velocities and wavelength? The mu2 by mu1. Mu and v, what is the relation? Inverse relation. So mu2 by mu1 will be equal to what? v1 by v2. v1 by v2 will be equal to what? Lambda 1 by lambda 2, because velocity and wavelength is what? Direct relation. Okay, so this is how we will be able to understand the relation between the refractive index and the velocity of the light and the wavelength. Okay, so wavelength, this is important, as I said, not so much when we are discussing about the ray optics, because in ray optics we will not talk about the wavelength much, right? Wavelength will be important when we are analyzing the wave optics. That's why I am covering it here, so that when we go to the wave optics, right, we will be able to see the relation straight away. Okay, so we are able to now understand in which case the light will bend towards the normal, in which case it will bend towards the normal when the light ray is entering from the rarer medium to denser medium. Okay, so how do we know which is the rarer medium, which is the denser medium? We will not directly know. We should be given the refractive index values. Maybe some of the medium we will remember. Like we know in comparison to any medium, right, air or vacuum or free space, for that the refractive index value is approximately close to 1. For the air or vacuum or free space, we will take the refractive index as what? 1. Which means in comparison to any other medium, maybe it is a water, it is a glass or any other medium, always the air is going to be what? Rarer. Always the air is going to be what? Rarer. So if light rays are entering from air to water, means what? They are entering from rarer medium to denser medium, right? Then they will bend towards the normal. Instead, like in this case, if the light rays are entering from water to air, means they are entering from denser medium to rarer medium. When they go from water to air, means they will be bending away from the normal. Okay, so this is what is the understanding of how we will be able to know whether the light rays will bend towards the normal or away from the normal based upon the refractive index values. So how refractive index values will determine? Refractive index values will tell us comparatively, because here we are comparing a medium to another medium. So comparatively, whichever medium is having a lesser refractive index, that will be called as what? Rarer. Whichever is got a higher refractive index will be called as what? Denser. Okay, it is a comparative thing. Say for example, if I have a medium with refractive index of 1.5, another medium 1.8. In this case, what you will say? The 1.5 one is the rarer medium. Okay, I'll give you one more example. I say that there is a medium with refractive index 1.8, another medium refractive index 2.4. When you compare these two, right? When you compare these two, what you will say? Which is the rarer? 1.8 is the rarer. So always a denser and rarer is comparative term. Tensor and error is what always comparative term. But if you take air or vacuum or free space compared to anything, that is always the rarer medium. Okay, so this is about the idea of the refractive index. But here you should note one thing. We are not able to tell by exactly how much value it will deviate. Okay, it bends towards the normal or away from the normal, we are able to understand. But by how much? That we are not able to know here. And we will be able to know that by using the law of refraction. So we'll go there, but before that, right, we'll just look at these sample questions. So these are very basic questions. Maybe you will be able to just like that give the answers, but in JEE or NEET we may not be able to expect this level of questions. Okay, unless the paper is set like NEET 2020 paper. I mean, if the paper is that much easy, right, then we may expect some questions like that. But generally we will not be able to expect questions on such basic things. So look at this question, guys. Refractive index of glass with respect to water is what? 9/8. Refractive index of glass with respect to water is what? 9/8. Refractive index of glass with respect to air is what? 3/2. Find the refractive index of the water with respect to air. So this is that relative refractive index concept, right? Look at this. What is the thing? So first we'll just write down whatever they are giving us. Refractive index of the glass with respect to water is what? 9/8. Means what? Mu glass by mu water. What is it? This is given as what? 9/8. Refractive index of glass with respect to air means what? Mu glass by mu air. Already we know mu air is what? 1. This is what? 3/2. Using this data, we have to find refractive index of the water with respect to air. Means what? We have to find mu water by mu air. That ratio we have to find. Check it up, guys. It's a straightforward question. How do we get it? How do we get this one? This is like the first ratio. This is like the second ratio, right? I think first ratio we have to reciprocate. We have to inverse and then multiply with the second ratio. Inverse the first ratio. Inverse means what? If inverse, what we'll get? Mu water by mu glass is equal to what? 8/9. We have to multiply this with the second expression. If you multiply means left hand side, what will come? Mu water by mu glass into mu glass by mu air. So mu glass is cancelled. Right hand side, what do you have? 8/9 into 3/2. 3 ones are, 3 threes are, 2 ones are, 2 fours are. What is it, guys? Answer 4/3. Check it up. I'm sure you would have got the answer for this one. Okay. So I'm yet to see any responses. Arun, Neelambari, Tara, Shraddha, Shyam. Okay. So maybe you can just type the answer there. What is the answer for this one, guys? It is what? 4/3. That is what? The refractive index of the water with respect to air. Maybe some of these common refractive index values, right? We can remember, like look at this glass. What is it? 3/2 means what? Approximately 1.5. Water, because glass means it is not like one glass. Glass itself, we have different types of glasses, right? And what about the refractive index of water? It is what? 4/3 means what? Approximately 1.83. Okay. Look at the next question. In a medium with refractive index 2.4, means for the particular medium, what is the mu value? 2.4. By the way, guys, refractive index, right? It's a ratio. It is what it is, a ratio, right? So it will be unitless and dimensionless quantity. What is refractive index? It will be unitless and dimensionless. It will not have a unit. It will not also have a dimension. Okay. So in a medium with refractive index 2.4, frequency of the radiation is what? 1.8 into 10 power 14 hertz. What is the frequency of the radiation? 1.8 into 10 power 14 hertz. Okay. Now look at the question. What will be its frequency and wavelength in air? They're asking what? what is the frequency of that same radiation and the wavelength in the air. See here, we'll just have to recall what we just discussed before. When light or any radiation, see, we are using the word light, but the same principle can be used for any electromagnetic radiation also. So when the light or the radiation is moving from one medium to another medium, frequency is not going to change. Means what? Whatever the frequency given to us, that is going to remain as it is. Means frequency in air, what is it? 1.8 to 10 power 14 hertz. It is not going to change. Then what is they are asking? Wavelength in the air. See, we know speed of light in air is what? 3 into 10 power 8 meter per second. Means what will be the wavelength? What is the wavelength value? Speed divided by frequency, right? Means what? 3 in 10 power 8 divided by 1.8 in 10 power 14. It will come in terms of SI unit meter, okay? Because both speed is in SI unit and frequency is also in SI unit. So look at this, guys. What will be the answer? This is like what? 10 power 8, 10 power 6 will remain. 3 by 1.8 into 10 power minus 6 meter. Now we have to see there is a cancellation possibility. What is it? 3 by 1.8 means we multiply by 10 both sides, it will be what? 30 by 80 now. 6 5s are, 6 3s are. So 5 by 3 means what? It is 1.67. 5 by 3 means 1.67, right? So 1.67 10 power minus 6 meter. That will be the wavelength. So frequency is going to be as it is. And wavelength we will get it from by using what? Wavelength we will get it by using the relation. Okay. Now here you might be thinking, why then they are giving us the refractive index of the medium? So that is something that can be given. So in some problems we will see that some extra information will be given so that we will keep thinking about it. And some of us, right, will try to force fit it. Maybe, you know, whatever the value we get right. I've seen some students, okay, it's a common mistake that some of us will do. We'll try to force fit. Maybe, you know, whatever the value we get it right, we'll try to divide this by using 2.4 like that. Okay, but we should not do that if we are clear in terms of the concepts. What is it, guys? The wavelength we will be able to simply get it from the speed of the radiation in that air and the frequency. So we don't require this 2.4 value. That is an extra information that is not required for us. Okay. So I'm assuming all of you would have got the same answer. So we'll proceed to the next idea. What is it? The idea that how do we know by how much angle this deviation is happening? Means the light ray is bending towards or away from the normal light. By how much it bends? We will be able to understand that from the law of refraction, which is also called as what? Snell's law. Law of refraction is also called what? Snell's law. So look at this. We have medium 1 and medium 2. When the incident ray is coming from the medium 1, incident at the point. This is the refracted ray. This is what? The incident ray, that is the refracted ray. This is like the normal. Now remember we said in case of the law of reflection, first thing is what? The incident ray, refracted ray and the normal all will be coplanar. We have the similar relation in case of the reflection also. There what is it? Incident ray, reflected ray and normal, they will be coplanar. Here incident ray, refracted ray and normal will be what? Coplanar. Here the angle of incidence we are representing by the symbol I. Angle of refraction we are representing by the symbol R. The relation between them will not be I is equal to R. In case of reflection, right, what did we have? Angle of incidence is equal to angle of reflection, but here it will not be there. What is the relation? The relation will be in terms of the refractive index values of the medium. The relation will be in terms of the refractive index values of the medium. So sine of the angle in a medium, we look at the angle. So medium 1, what is the angle made by the ray with the normal I? Sine of that angle into refractive index of the medium. That is going to be equal to what? Another medium. sine of the angle into refractive index of the second medium. This law, right, is what we call as the Snell's law. What is the law called as? Snell's law. So if you look at it, right, we rearrange sin I by sin R. We will get the sin R to the left side. Sin I by sin R will be equal to what? Mu 2 by mu 1. What is mu 2 by mu 1 means? Refractive index. What is mu 2 by mu 1 means? Refractive index of second medium with respect to first medium. What is mu 2 by mu 1 means? Refractive index of the second medium with respect to first medium. So from here we will be able to know, because this is a relation in terms of the angle, right? We will know exactly by how much the deviation is happening. Okay, so what is the relation? Sometimes, you know, this relation may be confusing. So you can remember this one. That will be very easy to remember. Any medium, right? The angle made by the ray, light ray with the normal, sine of that angle into refractive index of the medium, that is going to be remaining constant. Second medium means what? Sine of the angle there, sine R into mu 2. So sine I into mu 1 will be equal to what? Sine R into mu 2. So from here we can also get a relation like this. Sine I by sine R is equal to what? Mu 2 by mu 1. Refractive index of the second medium with respect to first medium. So this is how we will be able to know exactly by how much we are having the deviation. Now this is what we were discussing a little while before, right? What is it? If you have the light ray entering from the rarer medium to the denser medium, what do we observe? This is the original path. This is the original path, right? You can clearly see that from the Snell's law relation, right? What is it here? This is mu 1, this is mu 2. So mu 1 will be less than mu 2, correct? Now sine I by sine R is equal to what? Mu 2 by mu 1. Okay, so look at this. What is the mu 2 value higher? Mu 1 is lesser, right? Means mu 2 by mu 1, this quantity will be more than 1. Sine A by sine R is more than 1 means what? The sine angle will increase with theta. Sine theta value will increase with theta, right? Sine 0 is 0. Sine 90 is what? 1. Means sine value will increase with theta. So if sine A by sine R is more than 1 means what? We are saying sine A is more than sine R. That will imply what? I value will be more than R. We can see that, you know, the ray will be what? Tending towards the normal. That's why R is less than I. Instead, if the light ray is entering from denser medium to rarer medium. Okay. So here what is it? Mu 1 is more than mu 2. So this is mu 1. So here look at it. What is the relation? Sine I by sine R is equal to what? Mu 2 by mu 1, right? Here mu 2 is lesser. Means mu 2 by mu 1 will be less than 1. Means what? Sine I will be less than sine R, which means what? I will be less than R. This is the second case. Okay. So that's how we will be able to know using Snell's law also how the bending will be happening. But Snell's law, it is not just about telling whether it is a bending towards the normal or away from normal. It will also tell us by exactly how much amount it will bend. Because if you are able to know what is the R value, right? If you are able to know what is the angle of reflection, we will know exactly by how much it is bending. Okay. So this is about the idea of the Snell's law, and this will be useful for us while solving not only the basic level questions, but even some of the derivations that we are going to do in refraction, right? We'll use this Snell's law. Okay. Look at this question. So we are going through some very basic questions. From the given diagram, right? Find refractive index of the medium 2 with respect to medium 1. So this is say mu 2. This is mu 1. What are they asking us to find? Refractive index of the medium 2 with respect to medium 1. Means they are asking mu 2 by mu 1 value. Look at this, guys. It's a straight question, right? Snell's law question. I is what? 60. R is 30. What is the formula? Sin I by sin R is equal to what? Mu 2 by mu 1. This is what they are asking, right? Sin I means what? Sin 60. Divided by sin R means what? Sin 30. Correct. Sin 60 is what? Root 3 by 2. Sin 30 is what? Half. 2 is cancelled. Check it up, guys. What is the refractive index of the medium 2 with respect to medium 1 root t. We can also write it as what? If you want decimal number means 1.732. If you want the value decimal number means what we can write 1.732. Okay. Hope it is clear, guys. Let us go to the next question. A ray of light falls on a glass plate of refractive index 1.5. So the ray of light is falling on a glass plate. What is the refractive index of the glass plate? 1.5. So here they are not saying from where the ray is coming. So in those cases, right, we will have to assume that the ray is coming from air. So whenever they generally say that okay, the ray of light is falling on a glass or something, what is the assumption? You have to assume that the ray is coming from the air. Okay. What is the angle of incidence of the ray? If the angle between the reflected and refracted rays is 90. So here we need to understand one thing. Like, you have, this is the glass. Okay, so let us just represent the normal. I'll use a different color marker. So let us say this is the normal. This is the normal, okay. We have the incident ray. So this is the ray incident is coming from where? Air. It is coming from there. This is the glass. Glass refract, this is what 1.5. Now incident ray is coming like this, imagine. Okay. What will be the reflected ray? That will be the reflected ray. See, whenever we have the light ray which is falling at the interface. Interface means what? One medium to another medium. The surface is also called as what? Interface. There will be not only the refraction part. Refraction means what? The light rays will go to other medium. There will be also some amount of reflection. So both reflection is going to be there as well as the refraction also. Okay. Now look at this. The refracted ray. So this is the incident ray and a reflected part. Refracted ray. Refracted ray means what? Since it is going from air to the glass, it will bend towards the normal, right? It will be towards the normal. Okay, it will bend like this. Now here, this is the refraction angle. This is the incidence angle. Because angle of incidence is equal to angle of reflection, right? This is I, this also is I. What is the condition they are asking? What is the angle of incidence of the ray if the angle between reflected and refracted? So this is reflected. This is what? Refracted. The angle between reflected and refracted is 90, means this angle is 90. Further, they are asking what is the I value. For that given condition, they are asking what is the I value. Now look at it. I, this is 90, this is R. All the three angles are forming angle on a straight line, correct? Which means what? I plus 90 plus R is equal to what? Angle on a straight line is what? 180. Understand one more time? What is it? This is I. This is 90. This is R. All three of them are forming angle on that straight line, on that normal line. Which is what? The total sum will be 180. So here 90 will cancel, which means what? I plus R is equal to 90. Otherwise, R is equal to what? 90 minus I. The refraction angle is what? 90 minus I. Now we will go to the Snell's law. What is Snell's law telling us? Sin I by sin R is equal to what? Mu2 glass refraction index 1.5 divided by mu1. Air is what? 1. So sin I divided by sin R. Sin R means what? Sin of 90 minus I. What is sin of 90 minus I? Cos I. So in place of sin R, what we can put? Cos I. So sin I by cos I is equal to what? 1.5. What is sin I by cos I means? Tan I. So tan I is equal to 1.5. Here I will be equal to what? Tan inverse of 1.5. Even in the options also we will have like this only, because we will not be able to exactly tell what is the value of that angle. If tan theta is equal to 1.8, can we straight away say that angle is this much? We will not be able to say, okay, unless the tables are given. We may approximate it. We can approximate it, but we will not be able to say. Okay, so clear. So this is what the angle of incidence for which the reflected ray and the refracted both will be perpendicular to each other. So if you want to approximately tell what will be the angle, think about it. Tan theta is equal to 1 means theta will be 45. Tan theta is equal to root 3. Root 3 means what? 1.732. Then theta will be what? 60. Here tan theta is coming as 1.5 means the angle will be between 45 to 60. That is something that we can approximate. Okay. So this is how we'll be able to solve questions like this. Okay, good. Siddharth, you are saying 56.3. Okay. So this is how we'll be able to solve questions based on the basic idea of the refraction. Okay. Now, when we have like series of medium, we can also call it as what? The sequence of medium or series of medium, like one after another. So medium 1, refract next mu1, medium 2, mu2, medium 3, mu3, medium 4, mu4, medium 5, mu5, like that. We keep them in arrangement. So these kind of questions will be of interest for NEET exam, because here we will not have so much of numerical intensity, but this is going to be just based upon the concept. So here if you have like multiple medium in between, can we know what is the relation between this I1 and I5? I1 means what? The angle in the first medium. Here I2 will be angle in second medium. I3 will be angle in the third medium. I4 is the angle in the fourth medium. So we will be able to know what is the relation between this I1 and I5. How? See, one by one medium we will just go through. First medium to second medium, there is a refraction. Here what will be the relation? Sin I1 by sin I2. That will be equal to what? Mu2 by mu1. Here, second refraction. So we're done with the first refraction. Second refraction. Look at this. Here angle is what? I2. Here angle is what? I3. Now, sin I2 by sin I3 is equal to what? Mu3 by mu2. Then we'll come to third refraction place. This is from medium 3 to medium 4. Sin I3 by sin I4. That will be equal to what? Mu4 by mu3. Then we'll come to the last refraction part. Here sin I4 by sin I5. That will be equal to what? Mu5 by mu4. Now when you multiply all these four expressions, just multiply all the four expressions, what we'll have? Left hand side we'll have to multiply. Similarly, right hand side also we have to multiply it. Look at this. Sin I2 will be cancelled. Sin I3 in the denominator, sin I3 in the numerator, cancel. Sin I4 in the denominator, sin I4 in the numerator, cancel. So left hand side will be simply what? Sin I1 by sin I5. Right hand side, look at it. Mu2 in the numerator, mu2 denominator. Mu3, mu3. Mu4, mu4. You know what will be remaining? Mu5 will be remaining in the numerator. Mu1 will be remaining in the denominator. So this is how we will get the relation between angle I1 and angle I5 when we have a series of medium or sequence of medium. Okay. So this relation will be useful for us. Just want to check if you guys are able to get the audio or not. Okay, check it up, guys. Is there any issue with the audio or? Okay. Okay, guys. So we'll move on to the next part. So maybe I was a little bit distant from the mic, I guess. That's why there could be some issue with the audio. But we will move to the next segment. The idea of total internal reflection. See, previously what I was talking about whenever the light ray is falling on that interface, what I said, there will be some amount of reflection, some amount of refraction. Okay, so like, here, look at this. When we are incidenting the light ray from denser medium to rarer medium with an angle of incidence I. So we'll see that a part of the light will be reflected and a part of the light will be refracted. So remember, the light ray, when it is going from denser medium to rarer medium, how the light ray will go? It will bend away from the normal, correct? The light ray will be bending away from the normal, which means in this case R will be more than I. Now think about it. If we keep increasing I value, increase I value, R is more than I, means what? R also should increase. Just to tell you some numbers, right? Maybe let us say initially I is 45. I'm just telling some number. R is, let us say, 60. Make I as some 50. Maybe R will become 73. I mean, these numbers are not exactly correct, but just it will increase. If we make I to be maybe 70 or something, we will reach a situation where the R will be exactly becoming 90. Because R is always more than I, because we are looking at what? The light ray going from denser medium to rarer medium. So if you keep on increasing I, you will get a situation where the angle of refraction is what? 90. That particular angle of incidence, right, is what we call as the critical angle of incidence, theta critical. What is this? The refracted ray will graze. Grazing means what? It will go along the surface. It will graze through the surface. Refracted ray will graze through the surface. Okay, so that is what we call as the critical angle of incidence. Okay, now okay, now when we increase this angle of incidence further, what should happen? The refraction angle must increase further, right? If you just go by the Snell's law concept, incidence angle is increasing means refraction also should increase. The angle of refraction should increase, but it cannot increase more than 90. If it is increasing more than 90, means what happens? The light ray will no longer be in the second medium. Increasing more than 90 means what? It will come into the first medium itself, right? Which means what? If the angle of incidence is more than this critical angle, then we will not have any refraction. So there will be no refraction. There will be only what?
reflection. And this happens when we are incidenting a ray from denser medium to rarer medium. The phenomena of total internal reflection, right, will not be there when we are incidenting a ray from rarer medium, denser medium. This is only when we are incidenting the ray from denser medium to rarer medium. In that case, if the angle of incidence is more than this critical angle, we will see what is the critical angle also. If the angle of incidence is more than a critical angle, then we will be having what? Total internal reflection. This is something that will be used in certain applications also, but look at it. So how do we find out what is this theta critical? Look at this here. When the angle of incidence is theta critical, what is the angle of refraction? 90. Correct. So this is what? Denser medium, let us call it as what? Mu denser. Rarer medium, let us call it as what? Mu rarer. Okay, so now look at this. I'm going to use the Snell's law. Sin theta critical, because that is the angle of incidence, divided by what is the angle of refraction? 90 is equal to what? It will be equal to mu rarer by mu denser. Correct. So here sin 90 is what? 1, which means sin theta critical is equal to what? Mu rarer by mu denser. So from here we can find theta critical. What is it? Sin inverse of mu rarer by mu denser. So this is what is the critical angle formula. If the rarer medium is air, right, then what we'll have? Theta will be equal to what? Sin inverse of rarer medium is air, means for that the refractive index is 1, divided by denser medium will have some refractive index, let us say mu. Like that we will get what is the critical angle of incidence. So if the angle of incidence is more than this, means we will have what? Total internal reflection. So the light rays will not be entering into medium 2, they will be staying in the medium 1 itself. Even though they reach the boundary or the interface, they would not be going to that side, they will stay inside the medium 1 itself. Okay, so this interesting phenomena, right, will be used in some applications. We'll talk about that, but this is the concept of the total internal reflection. Now the optical fibers, right, which are used for the transmission, high-speed transmission of the data, etc. So they work on the principle of this total internal reflection. So the light rays will be, so optical fiber will be having a material, like even though if you check these data cables, right, the ACT fiber or all these things that are coming up, you just cut it and open. The data cable comes, cut and open it, right, you will see that it will be what? A thick wire. It will not have any hollow space inside, there will be thick wire. That is what is the optical fiber. So when light ray is incident on it, so this is what? The denser medium. Outside what is there? Air is there. Outside what do we have? We will have the air. Now when the interface is there, from the denser medium, the light ray is falling on that interface. Outside what is there? Rarer medium. If the angle of incidence is more than the critical angle, then what we'll have? We'll have that light rays will be just keep on getting reflected inside only. And this will be possible if you choose the material particularly. Like remember, theta critical will depend upon what? Here outside medium is air, right? So theta critical formula is what? Sin inverse of 1 by mu. You will select the material of the optical fiber such a way that the theta critical value, right, will be very less. Means what? It may be, say for example, 4 degrees or 5 degrees. Then what happens? Whatever the value of angle of incidence, right, you will generally have what? Total internal reflection. So the working of the optical fiber will depend upon what? The choice of material. You have to choose the material in such a way that the theta critical is what? Less, so that any angle incident, you will still be able to see the total internal reflection. Sometimes what happens is the optic fiber, right, will also have some outer covering. Generally, you have a fiber material like this, you will have an outer covering. Okay, so the outer covering also, like if you have an outer covering, right, for this, the material of the outer covering will be optically rare. Okay, so the outer covering will be what? Rarer. Inside Inside will be what? This is the denser. So we'll have the total internal reflection happening between what? The interface between that denser medium and the outer covering. Okay, so this is how the optical fibers will actually be able to work and transmit the communication. Okay. Now the total internal reflection phenomena, right, is also something that will help us understand the idea of visibility of a source which is placed in denser medium like water. I'm not sure if you may have experienced this practically. Like, think about it. You keep a light. You keep a light inside the water. Generally, what is the understanding we'll have? The light will be able to produce the light rays which will keep going in all different directions. That's right. So the light rays will keep going in all different directions. This is what we'll expect. So which means wherever you are, you will expect that you will be able to see the light rays. But it is not going to happen like that. You will not be able to see the light rays coming from all the places. The reason for this is the phenomena of total internal reflection. So look at this. If you see the light ray that I have represented, right? Think about it. If this is a ray, light ray that is coming from the source. If this is exactly incident at that critical angle, because this is water, right, and this is air. They are observing from the air. So light rays, when they go from denser medium to rarer medium, they will bend away from normal, right? So this is the critical angle. Now you pick up another ray, like the ray that will come later. For that, you see what is the angle of incidence going to be. You can see here what is the angle of incidence going to be. The angle of incidence here will be what? More than the critical angle. Means this ray will not get the second medium. It will get reflected internally. So there will be a total internal reflection, which means this will be the last ray that will be able to go to that medium 2. Here also we can mark correspondingly symmetrical one. So we keep a point source. Think about a point source, right? Keep a point source at the bottom. Then on the surface of water, you can actually, with this as the radius, right? You can think about a circular region. On the surface of the water, you can think about a circular region. Only the light will be visible through that part. Why the light rays will not be able to come through the other side? Because you see here, when the light ray is incidenting here, it is incidenting with an angle more than the critical angle. That is the reason why from the other places, right, you will not be able to see the light rays. Only when you are here in this circular area, that circular area only we will be able to see the light rays coming. Okay, so this is what we will be able to practically observe in terms of the visibility of a point source when we are keeping this in the denser medium. This is an important one for the numerical questions. We will see a question also on this, but we need to understand the idea. What is the idea behind it? The light rays, when we are incidenting, right, we can draw the light rays in whatever directions possible. But once the light ray is incidented at a critical angle, after that, whatever the light rays that we draw, they will not be able to go to medium 2. They get what? Reflected internally. Total internal reflection, which means only in that. So from that central line, if you consider this as R, you think about a full circular region with that radius. Only through that region we can see the source. Outside the region, we will not be able to see the source. Why is it happening? Because of the light rays coming from the point source. Beyond some point, they will undergo what? Total internal reflection. That is the reason why we will be only able to see the light ray to a particular region. Okay, so now we look at a question based on this. Maybe with this question we can see how the problems can be framed on that. Look at this. A point source is placed at a depth of 8 meters below the water surface. Means what? Remember, this is what we are discussing, right? So where we are keeping, this is the source. How much depth it is kept? 8 meters. A floating opaque. Opaque means what? No passing of light through it. Okay, a floating opaque disk is placed on the surface of the water. This means what? Circular surface is placed on the water so that the source is not visible from the surface. So we have to keep a disk on the surface of the water so that the source is not visible. Means we have to exactly cover that entire circular surface to which the light rays can come. Then if we are able to cover that region, means what? For anybody who is seeing from the surface, the source will not be visible from them. Okay. So a floating opaque disk is placed on the surface of water so that the source is not visible from the surface. Means we are seeing from surface means the entire region through which light rays can come to medium 2, that is being covered up by a floating opaque disk. From other part, the light rays will not come, right? So this is, like say for example, this is that line. This is exactly the theta critical line. After that, if you draw a line, means what? The angle of incidence is more than critical angle. So if you draw one more line from here, a point like this, here what do you observe? The angle will be more than the critical angle. So there we will not have any passing of the light ray to the medium 2. That will undergo what? Total internal reflection. Okay. So here this is the situation. Now the radius of the disk we have to find out. So what is asking? What is the minimum radius of the disk that is required to cover up this area? See, when I say minimum radius means you take a larger disk, means that also will be able to cover up, right? So the condition is what? We have to find out what is the minimum radius that is required for the disk to cover up all the light coming from the point source. Point source is sitting below. So here look at this R we have to find. What is this angle? Theta critical. This is theta critical, means this is also theta critical, right? Now look at the right angle triangle. Right angle triangle. What is the tan theta critical? Opposite by adjacent. So from here, what is that R value? 8 meters into tan theta critical. Just trigonometric relation. Based on geometry, we have a right angle triangle here, right? So this is theta critical, means this also is what? Theta critical. Tan theta critical is what? Opposite, which is R, radius of the disk. Radius of the minimum disk that you require. R divided by adjacent is what? 8 meters. How do we know what is theta critical? The light is going from water to air, right? They are giving us water. What is the refractive index? What is it? 1.5. So what is the relation we have? Sine of theta critical is equal to what? What is sine of theta critical? It will be what? The mu rarer by mu denser, correct? Which is what? Rarer medium here is the air. Denser medium is what? Water. What is the refractive index of what? 1.5 means 3 by 2. So look at this is 2 by 3. Sine theta critical is what? 2 by 3. But to get the R value, we will need what? Tan theta critical. Remember guys, sin theta is what? 2 by 3. From here we can find cos theta. What is cos theta? 1 minus sin square theta. That will be what? Root 5 by 3. Cos theta will be what? Root of 1 minus sin square theta, right? So root of 1 minus sin square theta means what? 2 by 3 the whole square. 2 by 3 whole square means what? 4 by 9. So 1 minus 4 by 9 means what? 5 by 9. There is a root. So cos theta will be what? Root 5 by 3. Then tan theta will be what? Sin by cos. 3 will cancel. What is it? 2 by root 5. What is tan theta? 2 by root 5. Okay. Now we'll just have to substitute. What is the R value? 8 meters into tan theta is what? 2 by root 5. So what is it? 16 by root 5 meters. That is what is the minimum value of the R that we will require. That is the minimum value of the R that we require so that we can cover that surface of the water, and after that we will not be able to see a point source from the surface. From the surface we cannot see the point source. Okay, so clear guys. So this is how we have to approach questions like this. So now look at these relevant models that we're solving, right? So in each of these cases, whatever the standard model that we are having, right, we should be able to keep a note of them. Okay, so we'll continue the discussion in the next session. So next session we'll start with some more applications of this refraction at a plane surface. So we have the concept of apparent depth and apparent height. On that area also we have got questions both in JEE mains as well as NEET. We have got questions in the previous years. So we'll start from there in the next session. Okay.